Hi everyone. I'm going to talk real quickly about hypothesis testing, okay? And to continue on with probability and sampling distributions, okay? Now, I'm sure everybody's heard of hypothesis to some degree, right? They tell you in elementary school, high school, and junior high that is hypothesis is an educated guess. Now, in a more academic sense, a hypothesis is making a causal statement, right? It's saying that an independent variable x has an effect on a dependent variable, right? So we want to test the theory. Hanging out with delinquent peers causes delinquency, okay? So that's independent. Uh, it's suggesting that this independent factor on its own is the cause. It has an effect on the amount of delinquency a youth is involved in, right? So hanging out with kids who smoke marijuana is going to increase the likelihood that this kid smokes marijuana, right? Or another one is that the cause of skipping school has an effect of poor academic performance. That's the dependent variable, right? Skipping school is the independent variable. So I want to suggest that that relationship exists. So that's a causal statement, and that's essentially a hypothesis, right? But in statistics, at a graduate level, y'all aren't really testing the hypothesis. You're testing the null hypothesis, right? So if you're working on your master's thesis, you got to know your null hypothesis. And this is what's assumed to be true. It's assumed that no relationship exists between variables. We don't make the assumption. Not until there's enough information to overwhelmingly convey that that's true, right? That hanging out with delinquent peers is going to cause delinquency. It doesn't happen in all cases and all that type of stuff. And until we assume that it's fundamentally true, and that's an assumption that's always taken to be a given, because there's kids out there that are going to be in environments where they're around a lot of delinquent kids, right? And they, for whatever reason, they're not involved in delinquency, or there's some kids who skip school or miss school a lot and do exceptionally well in school for whatever reason, right? So but what we are presuming is that the null hypothesis is always assumed to be true, right? It presumes that no relationship exists whatsoever. It assumes that hanging out with delinquent peers doesn't have an effect on delinquency. It assumes that skipping school doesn't have an effect on someone's academic performance. So it's essentially that no relationship exists, okay? And that's how it's annotated with the HO right here, okay? Just a small, that's how generally a null hypothesis is just annotated, okay? So science works by disproving the assumption that no relationships exist, okay? And that's how knowledge progresses, right? And that's how we move from the idea that the world's flat to it's actually round. And somebody had an idea that, everybody at one point in time knew that the world was flat, so uh, you sailed your boat across the ocean or out far enough, you're going to fall off the side of the world and you're all going to die. All that stuff, right? Until somebody tested it and then proved that, look, no, I can drive my boat completely around this whole thing, right? And then there's a paradigm shift and all that type of stuff, but that's a philosophical debate, but or a philosophical lecture essentially. Null hypothesis is what is being tested statistically. So we're really asking how likely it is that the null hypothesis is true given what our sample data tells us. So within there's going to be error there unless you have an entire population, and this comes back to inferential statistics and where we're going. If you're taking a sample of 1,000 kids and want to look at their marijuana smoking habits and compare it to, and make assumptions about 1 million kids in high school using that sample itself, um, you're really testing the null hypothesis, okay, whatever that might be at that point in time. So you want to make assumptions about an alternative outcome. So that's where the hypothesis that most people are familiar with comes about. Your educated guess, okay, your causal statement, your research or alternative hypothesis, and that's making the statement itself, okay? It's the assumption making a causal statement. It's the assumption, your alternative, your research hypothesis, is making that statement that, well, hanging out with kids who smoke marijuana is going to increase the likelihood that that kid smokes marijuana. So you want to either reject the null hypothesis or fail to reject the null hypothesis when conducting a test in a statistical manner, right? Now, as far as hypothesis testing is concerned, null hypothesis more adequately, there's two types of errors that can be made. A type 1 error, where you reject a null hypothesis that is essentially true, right? Right here. So this is the truth, and then making that statement. So it can be excessively problematic. It's saying that a drug is effective when it is not, right? It's saying that this Advil is going to cure your syphilis or something. And that would be an excessive thing. But that can be problematic when finding somebody guilty who's innocent in a court of law, right? So we have these thresholds in criminal justice. Y'all should be familiar with. Hopefully, y'all are. To convict somebody in a jury trial, they have to be guilty beyond a reasonable doubt, which would equate, if you quantify it, usually people use the reference of 95% certainty, right? That they're guilty, that they committed that act. But making the wrong determination there is type 1 error if they actually didn't do it, if they actually didn't break into that home or shoot that person or whatever. So a type 2 error could be perceived as being more cautious. It's failing to reject the false null hypothesis. So it's a report of no significance when there is actually one, okay? So you're saying that nothing occurred when something actually did, okay? Going back to the court example would be finding somebody who is actually guilty and letting them off, right? Or a jury determining that they're not guilty, right? In our government, in U.S., obviously we say it's perhaps better to let a guilty man go as opposed to incarcerating somebody who's innocent, who hasn't done anything wrong in the first place. But another example of that would be a problematic situation of that would be determining that a cancer drug is ineffective at treating cancer when essentially it is, and determining that it wasn't that good, it didn't stop cancer or something like that. The thresholds, obviously, in the medical field are much higher than they are in social sciences, and then what we deal with usually as far as research and that type of stuff. So how much chance are we willing to accept? There's a trade-off here. So if you increase the error margins on either side, or want to make it easier to accept a false positive or reduce that likelihood, you're balancing that, right? So if you're increasing the likelihood that the proof, beyond a reasonable doubt, from 95% certainty to 99% certainty to 99.9999% certainty, there's a range of folks who are going to fit into that domain that might get let off because they're determined to be innocent when in fact they're guilty, or vice versa. So there's a trade-off there in those types of errors. So it comes down to significance level, all right, and what you're willing to accept, all right, how much certainty you're willing to accept, and that's your significance or alpha level. You might have seen them as p-values in articles that you've read. The risk that we're willing to take in rejecting a true null hypothesis. If the alpha level is 0.5, we're willing to be incorrect 5% of the time. So this is your normal curve again. This would be your mean right here. And then out to here is actually 1.96 standard deviations. All right, it's close to 2 standard deviations, and we did standard deviation calculations already. So y'all should be able to do that for individual cases, but in the aggregate, it's a little different. But for right now, on either end of the spectrum, you can see that you reject here. There's 2.5%, 2.5%, and 95% falls within the critical region in 1.96 standard deviations. Okay, So if you want to reduce that, you can. If you move it to 3 standard deviations away, this bar out here moves out, and so does this one. And then you're including 99%, right? And if you want to go a step further, you get more of the samples, essentially. You're making it either stricter to adhere to these standards, okay? You want to, you're ensuring that the effect there, okay? In social sciences, we generally set the alpha level at 95% or 0.05. In hard sciences, where testing a new drug on cancer, if you mess up there, you can't be killing 5 out of 100 people. So they want their margins of error to be much less. Let's put it that way. So 1 out of 1,000 before the FDA is going to accept it, and all those types of things. So the critical region of a probability distribution, this is it right here, it defines the entire class of outcomes that will lead us to reject the null hypothesis. If a value falls in the region, we reject it. So if the jury determines that there's enough evidence within that 95%, they convict him as guilty. So your text kind of gets into a list of steps of hypothesis testing, so I'm just going to briefly hit it real quick here, so I'm not going to use too much time. But essentially, this is a good list to know, just kind of steps in research. First and foremost, you're going to start with a research question. Does hanging out with delinquent peers cause delinquency? So that would be a research question, I would say, and then you formally state the null and alternative hypothesis. The null hypothesis is that hanging out with delinquent peers has no effect on delinquency. The alternative hypothesis would be that hanging out with delinquent peers does in fact influence the amount of delinquency you engage in. So from there you determine the probability distribution you use. We're not going to talk about that too much. I'm not going to talk about it all in this chapter. You can have one-tailed or two-tailed distributions. Y'all don't need to necessarily worry about that. A one-tailed is making a directional statement, essentially. It's basically half. If you take this half away, and it's just starting there and saying that, yes, it does, all right? It's making a directional statement, or no, it does not, all right? Define the alpha level is the third step in determining what 0.5 accuracy, 5% of the population can be wrong, or 5% out of 99, out of 100, or 99 out of 100, this would be 1% right here, correct in that statement. So from there, that's defining what your alpha level is. That is defining your significance level. And then calculating, doing your statistical analysis and that type of stuff we're going to talk about later. And the final one is making a decision about it. So you either reject or you fail to reject the null hypothesis. You're not accepting, you're not proving that your alternative hypothesis or your research hypothesis is correct. You're rejecting or you're failing to reject your null hypothesis. And you're failing to reject it is when you're essentially, is what somebody's saying, is that your alternative or your research hypothesis is adequate or is true for that point in time. So standard normal distribution, area under a normal curve. We put everything on the same metric, okay? And as I talked about probabilities before, they range from 0 to 1, all right? So, and it's all going to fall within the normal curve, okay? And it's defined by two things, this normal curve, okay? It's defined by its mean and its variance, and we've talked about that, right? We talked about the variance itself and standard deviations. That's what these guys are here. So you got one standard deviation, two standard deviations, which you can see for two standard deviations is 97.7%. That's combining both these ends, okay? And from here forward, three standard deviations is 99.9%, and that's including from here to here. And one, you only get about 68% right here, okay? Hopefully that makes sense a little bit. All right. Now, how does this occur? How do we get everything on the same values? Well, essentially, when you're doing an analysis, you can determine how far away any case itself falls from the mean, all right, by getting a z-score, all right, so any individual case. So this is a standardized score. Why would I need a standardized score? Because sometimes you're measuring things in different metrics that don't mean the same things. Like if I'm looking at days or months or money or substance use, how many times you use substances or temperature, all those things have their same way of being measured, okay? And usually they refer to it as units, all right? The intent is to get it all standardized. So in this normal distribution here, the mean is 0, all right? And then we're either looking at plus or minus 1 standard deviation or plus or minus 2 standard deviations and everything in between there, and 3 and what extends beyond that 99.9% right here. Very little, okay? But this is how you calculate it. Your raw scores minus the mean over the standard deviation. And everybody should know what the standard deviation is at this point, and you can see where something falls on it, right? So I had this dice example here. If you have 2 dice, you can see if this is 99%, you know, the 12 and a 2, if you're rolling 2 dice, the likelihood of that existing within the 0 to 1 range, they're very far out there. But the likelihood of all the 7s, if you're rolling these dice 1,000 times, you're going to get a lot of 7s. You're going to get a lot of 6s and 8s and 9s and 5s, right? But even less 4s and 10s, and then even less 3s and 11s, okay? And this would be like within the 95%. And I know that's not true, but for this example, let's just play that it is, okay? So standard score is scored from the standard normal probability distribution that indicates how many standard deviation units a score is from the mean of 0. Okay, so how far away a value is from 0, either in a plus or minus direction. So 2 pieces of information that calculating the z-score, which is just the raw score itself minus the mean of whatever values you're looking at, divided by the standard deviation, and you can calculate that, and that's a fairly simple thing to calculate for any z-score. So it tells you whether the information you get from it either tells you it's positive or it's negative, right, from the mean, and the magnitude tells you how far away. So if you get negative 0.72, well, you know it's going to fall within this region, so within 1 standard deviation way. So if you get 0.198, then you're going to know you're just out the 95% confidence interval, okay, or 0.05 alpha, all right, and that's kind of where 1.96 is 95%, okay, on each end, plus or minus. So that's about it as far as z-scores and hypothesis testing, okay, and hopefully this stuff kind of comes together. So all right, let me know if y'all got any questions. All right, I'll talk to y'all soon.